What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we're going to continue talking about momentum and how to change momentum. But we're going to start with where we've been. So where have we been? We've discussed the theme of this course is that outside forces cause changes. And initially, we started by discussing how outside forces cause changes in speed. We called that F equals ma, right? They cause accelerations. We then talked about how outside forces can also cause changes in direction. We talked about circular motion, right? That force is tangent to the direction of motion. We see a circular motion or an elliptical motion. And then thirdly, we talked about how outside forces can cause changes in energy or mechanical energy. And we discussed that a change in energy is also known as work. And again, the underpinning, the underlying theme of this course is and will always be Newton's second law, that an outside force acting on a mass causes an acceleration or a change in motion. So we're going to start here, and we're going to kind of analyze and review a little bit on the second law. So I've got a scenario on the board, and I've got Newton's second law written down. So I've got a car driving down the road. It's moving to the right, and an itty-bitty bug over here is also flying down the road in the opposite direction of the car. Eventually, the car and the bug are going to meet. And when they do, the bug is going to splat on the windshield. But I want to think about a couple things. I'm going to think about some aspects of the car and some aspects of the bug that I can compare. So the first thing I want to think about is the force experienced by both. All right? So a couple aspects. I'm going to think about the force, I'm going to think about the mass, and I'm going to think about the acceleration of both objects, okay? So here's a little table I can create, and I can think about, all right, how does the force experienced by the car compare to that of the bug? Well, the bug applies a force on the car, and the car applies a force back on the bug. And because the bug's pushing on the car is pushing on the bug, we know that this is a Newton's third law pair. They're interacting with each other. There's a force between the two of them. And because of that, we know that the force acting on the car and acting on the bug are equal. The car's force on the bug is equivalent to the bug's force on the car, but pointed in opposite directions. This is where that equal and opposite idea comes from in Newton's third law, okay? If I think about the mass, though, of each object, the car's mass is huge. It is much, 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 much larger, and the bug's mass is much, 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 much smaller than the car. So because the car is so massive that the force applied to it creates an itty-bitty, teeny-tiny, nearly negligible acceleration. This acceleration of the car as a result of the bug is so small. This is why as you drive down the road and mosquitoes and bugs hit your windshield, your car doesn't really lose speed. On the flip side, because the bug's mass is so little, the force that acts on the bug from the car results in a massive acceleration for that bug. It is so massive on the bug that the bug goes, its little exoskeleton can't hang on. It just totally breaks. And this is why bugs go splat on our windshield. And this is a way of explaining this phenomenon using Newton's second law. They experience the same force, but because they have different masses, they experience different accelerations. This is something we've already discussed in class. Let's think about this from a different vantage point, though. Let's go ahead and take Newton's second law, F equals ma, the theme of our course, and bring it over here. And let's rewrite it. Let's say F net equals ma. Let's replace a with its definition. Let's replace a with a change in velocity over time. And when I go ahead and do that, what I'm left with is F net equals m times a change in velocity over time. This is a new equation. It still works. It's still fine. Let's do some rearranging. I'm going to get F net times time over here and mass times a change in velocity over here. Now, one thing that we haven't pointed out yet, but I will, is that mass and velocity, when they are multiplied together, have a special name. This is inertia in motion. It's mass that is moving It is momentum. Mass times velocity is momentum. So I'm going to go ahead and rewrite this so that I have mass and momentum together, and I'm going to get this weird change in velocity thing out in front. So here's what I'm left with. I'm left with F net times time is equal to a change in mv. mv, as we say, or just said, mv has a special meaning. Momentum is equal to m times v. And you can go ahead and find that on your equation sheet. Momentum is a lowercase p, sometimes a Greek letter rho, based on what you read, which text you have. But this is our equation for momentum. Momentum is the value of momentum. The value of the inertia in motion is mass times the velocity of an object. If that mass and velocity quantity changes, we call that a change in momentum. So this term right here is known as a change in momentum. That's what this is. Over here, we can see that this change in momentum is the result of a net force. What do you know, folks? Forces cause changes. A force times time, or a force that acts during a period of time, is a change in momentum. We give this special case, this force times time quantity also has a name. It is synonymous with change in momentum, but its special physics name is impulse. Therefore, an impulse is equal to, or an impulse is a change in momentum. And this is kind of confusing, but it shouldn't be, because we've seen this before. We've seen this before with work. Last unit we said, hey, a change in energy is equal to work. And we said a change in energy is final energy of a system minus the initial energy of a system is equal to a force times distance cosine theta. We noticed last unit that if a force is applied during some distance interval, that an energy value would change. Well, now we're saying that if a force is applied over a time interval, the momentum of an object will change, or we'll be able to calculate the change in momentum of the object that is in motion or is coming to rest or whatever's happening. But this is our basis. The basis we have here is that momentum is mass times velocity. A change in momentum is a change in that quantity, and it's rare that we see a change in mass unless an object explodes, but it's rare for us to see that, especially in this course. Rather, we would typically see a change in velocity. And how does that change in velocity occur? Well, there must be an outside force that acts over a time interval. This is our idea of the impulse change in momentum theorem, or the impulse change in momentum idea. This is the basis of this unit. Okay? Let's revisit that bug and car scenario. Let's go ahead and think about the bug and the car. They interact. They have a similar force, the same force that acts on them. We said Newton's third law. Let's look at a couple quantities. Let's look to explain this car-bug phenomenon using the impulse and change in momentum. So we'll look at, again, force that acts between the bug and the car. We'll look at the time of the interaction. We will look at the mass of each object. We'll look at the change in speed or velocity of each object, change in velocity, and then we'll look at its change in momentum, and lastly, its impulse. So we'll go ahead and do this. We'll look at all of these. As we said previously, does the force on, or is the force in the car and the bug the same or different? We know it's the same. We've talked about Newton's third law. These are the same. We said that earlier on in this discussion. Now, the time of the interaction, the time that the bug and the car experience this force, is that the same or different? And very similar to the force, if the car is applying a force to the bug and the bug applies a force to the car, that time interval has to be the same. The car can't push on the bug if the bug isn't pushing back on the car. So this time interval is also the same. So we see here that force and time for both of those objects is equal. I'm going to skip ahead and say that must mean that their impulses are equal, because force and time is impulse. So they experience the same impulse. If they experience the same impulse, guess what, folks? they experience the same change in momentum. So I'm going to go ahead and say these are equal as well. But what is different? We've already said the mass of the car is huge. The mass of the bug is teeny tiny. If the car and the bug experience the same change in momentum and the mass of the car is bigger, well, the change in velocity of that car is going to be small. And the change in velocity of that bug is going to be big. So why does the bug go splat? They have the same impulse. They have the same change in momentum. And because of that, the heavier object experiences a much smaller change in velocity. And the bug with the much smaller mass experiences a much larger change in velocity. This causes the bug to absolutely splat on the windshield. This is the basic idea behind impulse and change in momentum. Now, in class today, we talked about two big scenarios, okay? The first was maximizing the impulse on something. What are some things I can do to maximize the change in momentum? And so here's a scenario. The scenario is I have some buddies, and we're going to go outside, we're going to go push the car like we did in the car push lab. But this time, I want to get that car moving as fast as possible. What would I have to do in order to get this car to move as fast as possible? Well, let's think about this. Slide this over here, get rid of my work thing. I've got myself and some buddies, and here's the truck. And we're back here, and we're looking to push on this truck to get it going as fast as possible. And you think to yourself, what would I have to do this? Well, I know I'm going to have to apply a force. I'm hoping I'm really, really strong. If I'm going to push across a flat surface, I want to be as strong as possible. So I want to push as hard as possible, and it can't be quick. I need to push for a long period of time. So I want to apply a force to maximize impulse, to I need to maximize the force on the that I apply to the object, and I need to maximize the time that I apply that force. If I go ahead and I push really, really, really hard, and I push really hard for a long period of time, I am not going to end up changing the mass of the truck, but what I will end up changing is the speed or velocity of the truck. If I push really hard for a long time, eventually that truck is going to be going very, very, very quickly. So to maximize the impulse on something, to change something's velocity as much as possible, you need to apply a large force over a long period of time or a longer period of time, and this will cause us to see a larger change in velocity. This is one case that typically shows up as maximizing impulse. The second case that shows up is something that has a constant impulse. Meaning I'm looking at two different scenarios, typically stopping something. Typically stopping something is where I see a constant impulse. And I want to think about this. If impulse is constant, meaning the mass on something and its change in velocity is the same, I'm bringing something from some speed, initial velocity to a stop, that change in momentum is going to be constant, which means the impulse is constant. So if I think about an object, let's say you jumping up and down. I'm going to jump up and down, okay? I'm here, I'm going to jump up, and then from the top, I'm going to end up falling downward like this, towards the ground. Here's the ground right here, okay? When I hit the ground, I'm going to be moving. My mass is moving at a speed. I'm going to try to bring myself to a stop. So we're thinking about the collision, the force that the floor applies on me while I stop. This is what we're thinking about. If I think about how I'm going to do this, and you can try this at home if you're in good shape and no lower back problems, but at home, do this. Go ahead and jump as high as you can at home and pay attention to how you land. If you land, or when you do this, most people are going to jump and land and bend their knees. Now they bend their knees. They bring themselves to a stop. They bend their knees. Almost never is someone going to jump as high as they can, lock their knees, and land hard. No one typically does that. Our bodies aren't designed to land that way. Our bodies are designed to protect ourselves naturally. We would never land and think, I'm going to lock my knees as I land because this feels safe. That's not something we do. But let's imagine we did. Let's imagine we go ahead and take two scenarios. We have mass where these are the same. If I go ahead and bend my knees, if I think about bending my knees, what am I doing? What am I doing? Well, the time it takes for me to go from moving in the air to stopping on the ground increases, right? The time it takes me to come to a stop while I bend my knees is longer. I'm moving down still. I'm absorbing the landing with my knees. What that means is when I think about the impulse, I am increasing the amount of time. And because I've increased the amount of time that I'm bringing myself to a stop, it is going to require a much smaller force to act on me to bring me to a stop. I've increased the time. I can use that time and less force to change my momentum to slow me down. Now, if you lock your knees, something that we're not programmed to do, we do not naturally lock our knees when we land. If we plan to do this, that means we are stopping almost instantaneously. We're moving and coming to a stop very quickly. And when we do that, we're minimizing time, which results in a much larger force being required to stop me. That's why if you do this at home and you do it on a hard surface, you're going to feel like a jolt go up your back, through your hips and up your spine. You're going to be like, oh, that kind of hurts. And the higher you jump, the more it's going to hurt. So don't do it. Do not do this. Our bodies aren't designed to do that. Your spines aren't designed to do that. Don't do that. You're going to hurt yourself. But this is an example of a fixed impulse or a constant impulse in which controlling time will dictate a large force applied or a small force applied on an object. These are two primary cases that we see. Either we can maximize impulse by increasing force and length of time of that force, or with a constant impulse, we can see two different outcomes from the same scenario based on the time we apply that force over, or the time it takes to change our momentum by that fixed value. These are the basic notes behind momentum and impulse. These are some of the demonstrations we did in class, some of the notes we took in class. If you have any questions about what we're saying here, what I'm saying here, or any further examples that you would like to discuss about impulse and change momentum, drop it in the comments, send me an email, ask me in class. But until next time, see ya!